We return now for part 3 of my interview with Dr. Chad Brown.
So in some work that we've been trying to do together, or rather where you've been tutoring me in a lot of aspects of math and higher order logic, you've been applying set theory in the service of encoding some stuff about higher order logic, in particular how it relates to the work that I've done in Sumo. Can you say, in a non-technical way as possible for our listeners, what are we trying to accomplish? How does set theory help? How is it relevant to work in higher order logic and higher order logic automated theorem proving?
Okay, so I can sort of interpret this different ways. Let me answer both ways I can interpret it. So one is, well, what's the difference between set theory and higher order logic, right? And I think there it's fair to say, first of all, set theory has a long history. It's, in some sense, you could say mathematicians are all working in set theory, or almost all mathematicians are working in set theory, right? There's this famous quote from Hilbert saying, "No one shall expel us from the paradise Cantor has created," right? So yes, and in fact, one of the early interactive theorem provers, maybe they didn't call it that, but we can call it that here, is Mizar, which is based on a first-order set theory, and at one time had the biggest library of formalized mathematics. Really a pioneer, right, in terms of formalizing mathematics. So it's natural to consider set theory if you're trying to formalize mathematics. And if you're trying to do something that requires, if you're trying to formalize something that requires a fair amount of mathematics, it's a natural choice. So why are so many systems based on either higher order logic, like in terms of simple type theory or an extension thereof, or dependent type theory? Well, if you worked in, let's say, Church's simple type theory or one of the other kinds of type theories, you have beta, or at least you have beta reduction. You have lambda abstraction and beta reduction. Often you have more than that. And this is very convenient. So it makes your life a lot easier. So, but you also have set theory and higher order logic. Typically, higher order logic would be like a very weak set theory. Okay, so it's generally strong enough to do normal things you want to do. Okay, I can say more precisely, it's typically equivalent to MacLean's set theory, which is like Zermelo's set theory with bounded quantifiers. So, simply speaking, it's slightly weaker than Zermelo-Frankel without the Frankel. Okay. So you don't have replacement. And you can pretty easily build a model of this in ZFC. So it's weaker in terms of consistency strength. But it's strong enough to build the real numbers and do calculus and do, let's say, standard things like that, standard mathematical things. Okay. But you can't reason about abstract sets very well. Okay? And many people have extended their type theories in ways to try and make it easier to reason about, I'll say, abstract sets. But it's a question, if you're doing this, maybe you should be using set theory, right, instead of higher order logic. Okay, so that's kind of to say, what's the difference at a high level? But what we're doing, I'm working in a combination. It's set theory plus higher order logic, which makes it technically stronger than both ZFC and higher order logic. Okay? The nice thing is in higher order logic, you can write down the axioms, and there's only finitely many, so you don't have to deal with schemes. And so I'm using it because my interest is in formalizing mathematics. That's what I'll say about that. And then I'm trying to do something with you about translating Sumo into something with a formal deductive and semantics behind it, a deductive system and a semantics behind it. Okay? And that could probably be done in many ways. It wouldn't have to be done in higher order set theory. But I like higher order set theory, so that's probably one reason that's happening. But it also allows me to not have to worry about a lot of hierarchical issues. So I don't have to think about what type should class go to. In Sumo, you have a class. Well, you have lots of classes, one of which is named class, right? And one of which is named entity, which is generally the biggest class, let's say. So the simplest thing to do is, from my point of view, is translate everything to set, and then let the set theory sort it out. Okay? So if you were translating type theory, you'd have to spend a lot of time. Well, which things should be predicates and which things should be objects, and well, do we need two levels of predicates, and so on, which you could do, and there may be some advantages to doing that, but it's not so easy to decide what to do. And I think right now we want to do the simplest thing. So I think the simplest thing is just go to set theory. Okay, see if we can map this into set theory. Map sumo into set theory. And one high-level reason for doing this is it's like giving a Tarski semantics to the language, right? So that seems like a first reasonable thing to do. And at the moment, at least, we're committed to interpreting instance in sumo as membership, which also seems like a very reasonable thing to do, and subclasses being subset. And the relatively new thing we're dealing with is the kappa operator, which is a class formation operator. If we're interpreting things in set theory and instance as membership, you can just use separation at the set theory level. So you just form the set of all x, member of some universe, which I won't talk about, okay? Probably something with reasonable closure properties, and a set with closure properties, such that the thing underneath the kappa holds, so that the property holds. So it can allow you to deal with these kind of things that you can't deal with in first order. So if you were translating in first order, you might be able to deal with them translating into a type theory instead of a set theory, but it's not as obvious how, and it's not even obvious in set theory. So it gives me a lot of freedom about how to interpret and then sort out the details later.
Wow, so this is fascinating, and I've only begun to scratch the surface of understanding both your approach and the mathematical background of this approach. I guess I used to even think that set theory and operations on sets was something I would include in the ontology because it was something kind of relatively simple, right? You have sets and intersections and unions, and I had no idea that there was this whole other world that was so powerful that you could do things the other way around of embedding this particular logical theory inside set theory, and that it would be able to handle all of this and more. So,
yeah,
quite an education for me.
Yeah, I'm glad. So a lot of times when people use sets, it's at a fairly naive level, and I certainly think that can be put in sumo with no problem. And here you could just imagine that you have a collection of objects, like natural numbers, right? And you could talk about the subsets of natural numbers. There's there are interesting questions there, but nothing complicated there, right? You all can imagine like the empty set, or maybe you take the set of even numbers, the set of odd numbers, and union them up, and then suddenly you have all the numbers, or intersect them in an empty set again. But typically in set theory, you have sets of sets, right? And so the first thing you have to ask yourself, well, is there some bootstrapping problem here? Where are the sets coming from? And blah, 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 blah. This is not a mystery. There are different ways of doing things, but there are fairly standard ways of doing things too, where you start at the empty set, keep taking power sets, take infinitary unions, and basically, if you're in a well-founded set theory, which is very common, you can imagine the sets as being built up hierarchically, and would have essentially at every ordinal number a collection of sets that were born by this ordinal. Yeah, so there's a nice picture of a V you can imagine.
Okay.
And that's the kind of set theory where you can essentially encode practically all mathematics. And if you can do practically all mathematics, surely you can do, trivial things like, the physical universe.
Amazing. Okay. Well, fantastic. So I thought actually now maybe we could shift gears a little bit. This has been a very deep and technical discussion, at least for me and probably for our audience, even though it's of more tutorial nature for you trying to explain this area to us. I thought we could be maybe even a bit less technical and just ask, how did you get started in mathematics and particularly with higher order logic?
Okay, so I got interested in mathematics. Well, I was probably interested in mathematics even when I was very young. There's a story my mother loves to tell about when I was a small child, maybe 3 or 4 years old. And I didn't believe that there was no end to counting. So I decided to keep counting until I reached the end. It spent several days counting. So finally I just gave up. So it was like proof by exhaustion. I was like, okay, it never stops. Right? But then at university, when I was doing my undergraduate, I was computer science and mathematics, and probably more on the computer science side early on. And later on, definitely more on the mathematics side. Once I saw, proofs, epsilon delta, and group theory, you start to get this sense that there's a notion of truth out there that really is beyond anything we experience in this physical universe, right? And arguably is the more important notion of truth. So I got very interested in mathematics and logic. Where I was, there were no logicians, it was just mathematics. So I ended up in partial differential equations, and I was going to do a PhD in this, and I always had the feeling, taking like graduate level math courses, what I am doing, a computer should be able to do. Okay? And so secretly at night I would be looking at how do you represent these things in logic, and how would you use, well, at that point I was still learning what is a theorem prover, right? And so eventually I started playing with Otter, which was the major first order theorem prover at the time. Again, Bill McCoon, so no pioneer. And okay, well, how do you do mathematics? Well, you do it in set theory. How do you do set theory first order logic? Well, there's a problem. It's infinitely many axioms. This has already been considered in the 90s by Art Quaife. So at the time I was looking at this, Quaife's work was probably only 3 to 5 years old. It's relatively new. And very impressive, where essentially you're doing some math in Otter using Grunel-Bernai's set theory, finite. It's called set theory, it's really class theory. Because proper classes are objects. Okay? And very simple proof, the proof that the power set of x is always bigger than x, right? It's often called Cantor's theorem, or Cantor's theorem, I should say. I should know enough of German pronunciation to say Cantor instead of Cantor. But very simple result, very simple proof, very difficult to do in first order. So it was impressive that he was able to do this in first order, but reading the proof, you can see this is not the way to represent things. And so this led me to looking at Peter Andrews' work. This is basically Church's type theory, but he had a theorem prover TPS based on a form of Church's type theory. And I ended up transferring to Carnegie Mellon and doing a PhD in logic under Peter Andrews. So obviously he's the biggest influence on me in many respects, because I learned a lot while I was there. I learned a lot from him, and TPS, I got a lot of experience with TPS and actually formalizing some things. So I would say that's I'd say the key part to how I got started in this. Since then, I've certainly had a number of influences after the PhD. Like I spent 3 years working in Jörg Siegmund's group with Chris Bensmuller. We had a lot of fun out on his balcony. Let's say brainstorming about automated theorem proving in higher order logic. He's responsible for Leo, the resolution theorem.
And he was also Peter Andrews' student. Am I correct in that?
No, he was Jörg Siegmund's student, but he definitely spent some time in Pittsburgh. So that's where I first met him, was in Pittsburgh. The other person who I think was sort of in between, let's say I should mention, is Michel Kohasa, or Michael Kohasa, who He probably practically worked with Chris a good bit. Chris's actual advisor, I think, was York Siegman. I think Binsmuller credits Siegman as the one who got him excited about it. I think you did an interview with him, and he may have even talked about this, right? So Kohlhase, I spent a good bit of time with in Carnegie Mellon. He was there for at least a year, maybe two at the same time I was. And we spent a lot of time going through Hinkin semantics and variations of Hinkin semantics. Both of them, I would say, Kohlhase and Binsmuller, were key to me getting a good understanding of the semantic side of higher order logic and a good appreciation for it. And then after I worked with the Siegman group, I spent some time with Gerd Smolka's group. He's a programming systems guy. He's a professor at University of Saarbrücken, same as Siegman was. Smolka, I could say a lot of good things about. I think he probably is the person who has looked the most closely at my completeness proofs. And he and I talked about it a lot, and I think he made a lot of important simplifications to what I was doing. Very interesting time.
Yeah, I've certainly seen his name come up in the literature a lot. I mean, all the people you've mentioned are very big names, and so that's fascinating how these sort of progressions of students and studying, there's a real lineage to a lot of people in these fields where you learn from a master who's far, as an influence, far greater even than the seminal papers that they wind up writing. The direct contact with the students is sort of a beautiful transmission of knowledge over the generations.
Yes, I think this is true, and that's a very positive way of seeing it, which is, I guess, good. But people shouldn't get the wrong impression. Many times the progress is made by people arguing with each other.
Yeah.
And it might be, even if I say anything about anybody else's work, they might listen to this and say, that's completely misrepresented.
I've heard it often said that reading the summaries in Russell, for Bertrand Russell, of other philosophers in his history of Western philosophy, you get a certain view, and it's really better to treat that as a list of references and then go back and read the originals, because every scientist, every researcher, every philosopher has his or her own filter on the prior work of others.
Yes.
And maybe also related to the quote you were saying earlier, that it takes sort of deaths in the field, as it were, for fields really to advance and change, because people get attached to their ideas. Even scientists do, much less your average person is always very attached to his or her ideas.
It's completely natural.
Yeah. Wow, great. Maybe we could further go on this track of sort of lineages, and also talk about what are both some recent advances in the past just few years. I mean, you've certainly talked about a lot of stuff that goes back much farther than I would have thought. So thinking about higher order logic going all the way back to Frege, or thinking about automated theorem proving going back to the 60s or the 70s, when, just as a practical matter, people were doing things on punch cards and paper tape. It's really kind of hard to imagine. What are things that have happened recently? And then maybe you can keep going and say, what do you think are some frontiers for the future that either you're working on or your colleagues are working on, or maybe even things that people aren't focusing on that you wish there were more activity on?
Yes, this is a good question. So I worked on automated theorem proving for quite some time, and probably my biggest success was Satellax. But I would say in the last 10 years, I've focused more of my time on formalizing mathematics. So the fair thing for me to say is I probably don't know all the most exciting things that are happening recently, but I can give some highlights that I'm aware of and encourage people to look deeper. But before I do that, maybe I will fill in some gaps, because yes, it was Frege and it was Church, but in terms of automated theorem proving, in higher order especially, it would be a shame not to mention Gerard Hewitt. Okay, he's French, so I'm sure it's Houet. But if I say Houet, no one will know that I'm trying to say Gerard Hewitt, right? who had a resolution system, at least on paper, in the 70s, and developed also in the 70s higher order pre-unification algorithm for simple type theory, for simply typed only calculus. Very influential work. And also the work of my advisor, Peter Andrews, who I mentioned before, who had this system TPS, groundbreaking, pioneering work on multiple levels, not just TPS, but in the 70s. He also considered a kind of resolution system, but most of his work was in what they called connection calculus. Okay? Similar to what was developed by Beeble in Europe. They also have a connection method. There are some slight differences, but it's largely the same idea. And and an important thing that happens in the higher order case that doesn't have to happen in the first order case is, well, let me say it this way. In first order, you can clause normalize. And just assume your entire problem is first order clauses. And typically you would do something like resolution where things stay clauses. In the higher order case, it doesn't work like this. You can clause normalize, but you're inevitably going to do something that makes it not clause normalized anymore. So then you would have to keep clause normalized. And arguably the better thing to do is not clause normalize at all, but just directly work on formulas that are not in clause normal form. And I think Peter Andrews was one of the pioneers in developing these kind of methods that work on non-causal problems. In particular, like connection method and expansion proofs were the big things. This is all like 70s, 80s, 90s. Okay? And a couple of things that weren't dealt with at that point were extensionality and a reasonable way to handle equality. So I mentioned earlier you can define equalities, when in a sense you don't have to handle equality. It becomes a quantifier. But practically speaking, if you try and do theorem proving this way, it's not going to work very well. So I would say it's the work of Causa and Ventimiller who mainly brought in extensionality. Extensionality meaning two functions are equal if for all, two functions f and g are equal if for all x, f of x equals g of x. Now, and that's one kind of extensionality. Other kind of extensionality, propositional extensionality, is two propositions are equal if they are logically equivalent. Now, first order, these things don't come up because you don't have types of functions and you don't have types of propositions, typically speaking. So, in higher order, you do have this, and typically you would assume these things. And really, a lot of work has been done about 10 to 20 years ago about how to effectively deal with this in theorem proving. So, it might seem like, well, what's the problem? But unification in the first order logic really depends on the idea that two things are equal if they are syntactically the same. So it's how can I make these two things syntactically the same? Once you start adding extensionality principles, well, is P syntactically the same as not P? Well, no. One of them has two more negations in the other. Are they the same? Yes, right? By extensionality. They're equivalent, so they're equal. So you have to find some ways of building this into your theorem proving procedure. And a lot of that work, as I said, was done by Colas and Spiller, and to some degree by me. And then the other thing is choice, whether they have a choice axiom. And I think probably I was the first one to build this into a calculus. Right? It's easy to have it as an axiom, but it's better if you don't have to have it as an axiom, if you build it in. So this is all historical. You asked about recent events. The most recent thing I mentioned was the choice thing. So the satellites, this is already like 10 or 11, probably 12 or 13 years ago now when I did this. And the thing I could say about satellites in this context is it's very different from, it's probably works in a very different way than most people would assume it does. Most people are familiar with like resolution and unification.
And we talked about both of these on this channel, and I've at least attempted to explain them.
Yes. And satellites at least in its basic calculus, uses neither of these things. It's not working on a clause-normal form. It's just working directly on formulas. And it doesn't use unification, at least by default, to instantiate. So it's a good question of how does it instantiate, but I won't get into that. And the other thing is, in first order, typically you would deal with equality by doing something like paramodulation, or the modern thing is superposition, right? And Satellites doesn't do this either. So you have to reason with equality without rewriting inside of terms. So interesting question of how you would do that. So Satellites really takes a very orthogonal approach to what's typically done in automated team proving. It's kind of surprising it was so successful because of that. But you try different things, you solve different problems. So recently, I would say the top tier improver is zipper position. The top higher order automated improver is zipper position.
We'll pause here and return in our next video for part 4 of my interview with Dr. Chad Brown.